Next up, next up is Vasilios, who will be giving us an update about ReFrame. Over to you, Vasilios.
Thanks a lot, Simon, and everybody for attending. So yeah, I'm gonna give a update on the progress we've made in ReFrame since last EasyBuild user meeting, where we have presented and also had a tutorial back then. So I will assume that I will assume some prior knowledge of ReFrame. I will just have like a short recap of what ReFrame is here. And then I will just go on the new stuff and expand on those. So for those that you haven't heard of it or you haven't played with it yet, is a powerful testing framework that allows you to write system and software stack regression tests and benchmarks for HPC systems. And you write your tests in a high level in Python and not having to care too much on the details and interactions with the system. So it's more of a declarative than a prescriptive way. The tests are quite composable, and I'm going to expand on this today. You can have multi-dimensional parameterization, test fixtures and dependencies across tests. And this is also accompanied from the tests run by an efficient runtime that submits multiple tests in parallel and monitors their execution and makes sure that concurrency limits are met and that the concurrency is kept high enough. There's several abstractions that make your tests quite portable. So there are different scheduler backends, module systems, support for different build systems and container runtimes. Important thing is built in the framework, there's also performance logging that basically can direct performance logs into various channels, such as logstash, Graylog, syslog, and so forth. So depending on your setup, you could visualize the timeline of performance results of your test. And another thing is that the framework does not require any elevated privileges to it, right? It can simply run on user LAN, so that makes it a priori, so it doesn't pose any major threat on that aspect. So we have a growing community that has been growing constantly. And we currently have more than 150 members in our Slack workspace. And we're quite active there, also in giving support and discussion on features and use cases. It's quite interesting, and I would recommend if you're using the tool, just join that, because you get support and you get in touch with the community and perhaps similar problems. We just inaugurated just after the Christmas break a bi-weekly community call. It happens every 2 Tuesdays at 4:30 UTC. Yeah, here is the link for the minutes. And of course, don't hesitate to open any bugs or feature requests on our GitHub. And if you're using the project or you're interested into it, yeah, please give us also a star. That's also good. So as I said, of the community, I mean, I have been showing a similar graph in the previous presentations, and you see that documentation, at least, is read across the globe, especially US and Europe. As you can see, we have some people also from India and Australia, which, yeah, roughly we have 200 to 300 unique readers monthly. So it gains some traction, and that's really makes us happy. So since last year, just before, yeah, it happens that we just before EasyBuild user meeting, we do a release. So I think just before our presentation again in the EasyBuild user meeting in 2021, we released ReFrame 3.4, and now last Monday we released 3.10. And here I've listed just some, let's say, major enhancements. There are many more, and I would say that it was quite a prolific year. And I'm going to go in the following slides and elaborate a bit on those. So we have introduced new syntax elements on how for defining tests, and especially parameters, which makes it makes tests a bit more extensible. It's also saves a bit of typing as well, and makes also, yeah, the test, you can combine them better. We have introduced, you can now generate dynamic Gitlab pipelines from your set of tests that you load, so you can run them within Gitlab. We have some JUnit XML reports, which again helps with CI/CD and reporting. You have now the ability of skipping tests dynamically, so decide on a condition while you run your test and just skip your test if you figure out that it should not run. Another important feature is that we auto-detect the processor topology, and that really helps with tests such as benchmarks that you don't have to associate with your system, like the number of cores or the architectures that is on your system. So that gets automatically detected and made available to the test. We've added support of using EasyBuild or Spack for building the test code and then testing it with ReFrame. So that's all in a single test. We're going to see some examples of these. And then another important thing is that you can now set test variables from the command line. I will show how this is beneficial. We added support quite recently of test fixtures, and in this release, we made the build phase also synchronous. So you can have multiple build jobs on the fly at the same time. And we finally introduced a new naming scheme for tests, and especially for parameterized tests and fixtures, because those that you have probably worked already and had parameterized tests, you would have seen those big ugly names that they were produced, and could mess up a bit with, it would lead to very large paths in the file system, and that could be sometimes problematic. We introduced this year the concept of test libraries, and I'm gonna talk a bit about that, and as well as we accepted a couple of contributions with different scheduler backends, which is thanks to the community. So I'm going on now with showing the different advancements. So at the top of this slide, there is how we used to write the test. So we used to have this definite, which, although I mean it's quite compact, we never liked them so much that you have to specify the definite, which sounds a bit like an internal thing, and it just doesn't feel so nice. So now we have a different way which you can completely get rid of that need, and you just specify your variables, your test fields directly after your class. There is quite some magic behind the scenes, because actually those two are equivalent within ReFrame. And then there's also a new way of writing if you don't want to use the sanity patterns, especially if you have more complex sanity checking. You could use decorate your validation function with the sanity function decorator. And the difference from the sanity patterns there is that this is executed at the sanity phase of the test. So all the information the test has run, its output is there. This practically you can immediately evaluate any deferrable expressions that you would otherwise have to use in the old syntax. So that's facilitates the way that you can add your validation test. Another thing is how you define performance metrics. You remember we had this perf patterns dictionary, which is still valid, but now you have the ability to decorate just a function that you call a performance function, and you just return you extract the performance metric from the output of your code. And then the framework takes care of assigning it a unit based on your specification, as well as assigning it as a performance variable. So here is an excerpt from the stream test that's in the tutorial, and there you can see how the various performance variables from the stream benchmarks and the various sub benchmarks actually are extracted. And the nice thing with this index is that it's composable. So you may have a test that defines some metrics, and then you extend the test with more metrics without having to go through and redefining those performance patterns dictionary. So it's quite extensible. One big change is the test variables. So now you can define, and actually this is how all the built-in fields of ReFrame tests are now defined. You can define your test variables. These will eventually become test attributes, but you can assign a type to those, and this will be dynamically checked. You can assign default values, or you can make a variable to be required. And that means that when you try to run the test or access that variable and this is required, then an error will be thrown. And that's quite important when writing tests that you want or libraries that you want to impose like a more strict way of writing the test, or impose which variables are necessary for the test to run. So in this naive example, we define 3 variables, x, y, z. X is of type integer, and since it doesn't get a default value, it's required. So somewhere must be defined later on in the test. X gets a default value, and then you can use, and then Z is a list of integers, and you can use that utility that we offer, that you can practically validate that what gets assigned to the Z variable here is actually a list of integers. Then the derived tests inherit practically all your variables, and they can just define them as here, the X, or they can convert an already defined variable to required. And why this is useful, for example, in the various base regression test classes, they define all the fields like num tasks, executable, all the attributes are also variables. So you can mark any of those as required, which makes that you won't be able to run the test if this is not defined. And I have here also inserted in that hook just at the bottom intentionally an error where I'm trying to assign 10 to the variable Z, which expects a list of integers. And basically that's quite useful when you write tests, because that avoids surprises and makes also the life behind the scenes much easier, because the types are guaranteed to, the variables are guaranteed to have the specific type. A big change is parameters, and there has been I really like the way now parameters can be defined. So in the past, a parameterized test was defined through a special decorator that was called parameterized test, which was actually producing a series of arguments to be passed to successive invocations of your test constructor. So your test constructor, like here, would have to take the link and lang argument, and the parameterized test decorator would generate those series of arguments. And those expressions, you can see it already, it's a bit cumbersome. You have to know really well the list comprehensions and how you expanded, what you expanded, what not. So every time I had to look it back and say, okay, let me figure out the syntax. Now this is much easier because you define different parameters, and actually behind the scenes with the parameter built in, as we call it. So you can define different parameters, and that behind the scenes creates a parameterization space. So here we have a two-dimensional parameterization space. One dimension is the link, which takes two values, static and dynamic, and lang, which takes the three values, CCP and F90. And this will generate automatically 6 different test cases. And then later on, the name of the parameters is available as a test attribute. So as I'm doing here, preparing the compilation, I'm setting the source path based on the self.lang parameter. Now, self.lang will, for each instantiation of the test, will have the value, except a different value that comes out from the parameterization space. So you get practically all the combinations. This is very, very useful to generate really large amount of tests, and especially if you want to do performance exploration. So, and you want to try different compiling with different flags, or try to submit jobs on pair of nodes and so on and so forth. I mean, it's quite useful. And here I'm going a bit on to showing how a bit it works. So again, parameters are inherited, and that's quite a cool feature as well. So the base test defines a parameter, and then we can derive from that and define another parameter. And the derived test now will be parameterized in 2 dimensions, in P and Q dimension, generating 30 test cases here. 30 tests, not test cases. Test cases, but it'll be even more. So it will generate 30 tests. And then the other cool thing with parameters is that you can change the parameterization space as you inherit. So here we basically redefine parameter P, and we completely override it. But for parameter Q, we inherit it, but actually we prune the dimension. And we say we only want from those values, those that are less than 5. So essentially here, the derived 2 tests will generate 50 tests. So this is quite flexible. Now, I'm going a bit back onto the discussion I've shown before with the variables and why they're important. So if you define an attribute of your test with variable, then you make that available also for setting it in the from the command line. And if you have a variable that is required in your test, you can set it from the command line, and ReFrame will be happy because you have defined it. Now, I think things getting together because you can have like a more generic test that you don't want to over specify it for a system that you don't know, but you want to keep it a bit generic and give some knobs to the users, and some of those knobs may be required, some of those may have default values, but you give the users the possibility to tweak the test right before running it. And for example, I have some examples here where minus s num task will set in all the loaded tests num tasks to 10, and then you can even scope it to a specific test family, because that would, if my test is parameterized here, you will get all the parameterized versions of my test to get the value of lumitask 10. Then you get another interesting thing, since I said that all the built-in attributes of regression tests in ReFrame are variables themselves. You can set them directly from the command line. So here I'm setting modules to be a list, spam and eggs, and variables, you set environment variables. So you can set dictionaries, you can set and generally aggregate types. And the nice thing is that the framework takes care of the conversion transparently. So this internally is going to be converted to a list of string. This is going to be converted to an integer and so on. And you can even have custom types, which you could have conversions if you define the conversion function. But another thing is that your test, you can define the valid system, valid program environments directly in the command line. I'm going to show you those later on when I talk about the test libraries. Now, another nice feature, quite powerful, is test fixtures. So fixtures, for those that you're familiar with, or you're not so familiar with the test frameworks, usually, I mean, you might have seen them in PyTest, for example. And usually a fixture is something that holds a resource, and it is associated with a scope. So since the base thing in the ReFrame is a regression test, fixture is also another regression test, except that it has some special properties. But any test can become a fixture of another test. It's a nice thing. It's very composable. So fixtures, they don't define valid systems and valid program environments. So, or they're just, it is just overwritten. I mean, so practically they inherit their valid systems program environments from the test that is using them based on their scope. I'm going to show examples to be more concrete here. And the nice thing also is that you can access them. As with test dependencies, you can access the fixture object and get access to all the properties of the test after it has run. And behind the scenes, fixtures are practically also posing a set of dependencies between different test cases. So eventually you end up with a DAG of tests. And each node basically has a scope as well, which practically defines its lifetime. So here I'm going to show a little example on with OSU benchmarks. So OSU benchmarks, you want to download them to fetch the sources, you want to build them, and then you want to run different benchmarks, bandwidth, latency, and perhaps other collectives, and parameterize those. So you don't want every time to compile the tests or fetching every time. So here I'm going to show that with fixtures. You could do it with dependencies, but with fixtures is much nicer and much easier. So here is the fetch OSU benchmarks, which is like a normal test. So we define the variable version so that we can control which version we can download. Executable options. We force it to be local too, so that it will always execute locally, but I'm not going to go so much into this. You can look in the tutorial. And we validate it. Then we have the build OSU benchmarks, which basically says, the important bit here is that, well, I want a fixture, name it OSU benchmarks, that basically it's the fetch OSU benchmark test here and give it a scope session. The session scope means that that fixture will be valid for the whole run session. So it will only be executed once and then be reused. Now, in order to build the test, now I need to basically untar the sources and copy it from the session. Sorry. So what we're doing here is we construct the full path by just accessing the fixture handle here, and then any attribute of that test. So we get the stage there, we get the tarball directory, we do the copy, and we just, with a prepared build CMDs, we just prepare our build script practically. Now, exact similar way, here is the run test, the bandwidth test, for example, where you have defined your valid systems and valid programming environments, your node tasks, etc. And you say the OZU binaries is a fixture that needs to build OZU benchmarks with a scope and environment. So that means that this fixture, the build OZU benchmarks, will execute it once for each combination of system partition and environment. So you will get, it will get compiled once for the GNU, once for the PGI, and once for the Intel environments here. And then you can run as many tests for OZU bandwidth, especially, for example, if we have parameterized OZU bandwidth. And as I showed before here, I'm preparing the run. And again, we're accessing the fixture and we construct the path of what we want to run. Now, the nice thing with fixtures and the more flexibility they give is that they can be, I would say I use the word concretized, because the tests in ReFrame, they basically generate different test cases from the same test. So for example, if I have a test on my laptop, might generate just 2 test cases, but on a system that have multiple programming environments, multiple partitions, the same test will be generate many more test cases. So that process, we also call it concretization of the test into test cases, which will actually run. So in this case, also I'm showing the new type of listing. So you get that OZU bandwidth test is going to run on the GPU system with the GNU environment, and it depends on the build OZU benchmarks fixture with scope Dane GPU plus GNU. That implies an environment scope, which will again run on the Dane GPU plus GNU combination. And the fetch, which by on itself, it depends on fetch OZU benchmarks with scope that gets the system name because it's a session scope, which again will run on the GPU plus GNU. And you see here that although the fixture build OZU benchmark will run on different partitions, and you see also different scope, you see the same test for fetch OZU benchmarks. And ReFrame has picked a random partition and environment combination and said, I'm going to run on the GPU plus GNU, the fetch OZU benchmark. Now, if I scope from the command line that I only want to run on PGI, then the session, so here I get the build OZU benchmarks, I get only one on the PGI version. And that's because the build OZU, the fixtures inherit the valid program environments from their test that uses them. But the fetch OZU benchmarks, which doesn't care where it will actually is going to run, we just pick the GPU plus PGI environment because it's irrelevant. This wouldn't be possible with dependencies, but with fixtures and scopes, it is. So that's the one of the cool feature of fixtures. So I'm changing a bit topic now. I'm showing a bit on how you could generate from a test session or for running a test session on a CI/CD pipeline, especially in Gitlab. We have added this new action, CI generate, that actually generates a child pipeline with one job per test. And those CI jobs have dependencies, and this option practically takes care of generating those correctly. And the state directories between the tests, because they're needed since you have dependencies, are cast between the jobs. So they're not even reserved as artifacts, because if you do that, then you probably hit your artifact limits in GitLab. And also another thing is that if you're using images to run your CI tests into, then this image in your base GitLab CI YAML is going to be propagated into the child pipeline. So you get the same environment where you run your test. So here is like a simple GitLab YAML where you specify 2 stages practically. You'd need at least 2 stages, one that generates the pipeline with this CI generates, and into a file which you use as an artifact, which for the next stage, which generates which runs the test. So here is I took one of the dummy examples which define a set of tests with complex dependencies, and this is how it shows up. Again, related to integration with CI/CD frameworks, we now are able to generate JUnit reports. So then you can get nice tables, since all of those tools like Gitlab and Jenkins interpret JUnit reports. Now you can have this type of reports where you can click on it and get some more info. Since we're talking about system regression tests and software stack regression tests, well, I mean, and JUnit is mostly and JUnit format was inspired from unit testing, so some fields might not correspond very well. So you have to inject some information in fields that they're meant for a different reason, but you would figure out that when it says stack trace and we give just the error message of why the test failed, it's more important, because if for us we gave a stack trace, it means that something wrong with the framework and not with the test. And the other limitation is that it cannot take into account multiple retries of the same test, and that's because of limitation of the JUnit format. And as I said, this mismatch of the purposes. Another feature is skipping tests dynamically. So now we have those 2 methods, skip and skip if, and which I showcase here in a naive way. So if you run the skip phase anytime as while the test gets initialized, either as a post-init hook like here or in the init function, then the test is not going to be listing. It's going to be filtered out before even getting listed. But then you can even, while running the test, you might decide, okay, now I'm going to skip the test because the information that I wanted, I could only get it while I'm running the test. And here, again, we skip the test if the condition, and you get a message like that. And at the end, you will also get how many tests were actually skipped. Another feature that perhaps I should hurry up a bit is automatically detecting the processor topology. So we're now capable of detecting the processor topology both locally and remotely. So then you can write really tests that they are completely agnostic. And for that, we use Spack for detecting the architecture. So then you can even tweak your test differently for architectures. Then we had written the code for topology detection, and it generates out the JSON file here that's being cast in this folder, which has all the information. And this is made available into your test through the current partition.processor variable, which then it has different attributes. And in this case, for example, I'm taking the num course in order to set the num CPUs per task in the jobs script that's going to be generated, as well as the OMP num thread. So I don't need to. So these tests can be adapted to any system and partition run without any change. And there is also this utility skip if no proc info, which will skip the test if no processor info was generated, because by default, we disable the remote detection, because remote detection can take some time, but it will only take time the first time you run on a new system partition. If you have run it before, then it will just pick the topology from that file. But the first time, since it has to submit a job on the remote partition, can take some time to initialize. Now, probably also interesting to this audience is that we have added integration with EasyBuild and Spack, meaning that you can use EasyBuild or Spack as a build system to build your code and then continue on with ReFrame in the run phase and test that code. And this was primarily designed for CI/CD workflow. So the idea that you just tested a whole recipe from scratch, also its dependencies. So if it fails during building, then ReFrame is not going to go further. But and then if ReFrame fails on run phase, then you saw, okay, something's wrong. But you can still leverage this for integrating it with software stack installation at the same time. We have debated a lot what would be the best solution, but we ended up on having like standalone as default, so that it doesn't generate any side effects. So if you're running the test and you don't want to install half of your software stack because the final step failed, and leave things behind just because the frame test failed. So by default, it's standalone. Everything happens in the test stage directory, but you can change that, and I can show that. And this feature assumes that EasyBuild and Spack commands are available. So here is a demo test for bzip2, where you say what's gonna. Here we're just taking bzip2 minus help. It's very naive, but you could have a much more meaningful test. You say EasyBuild, your build system EasyBuild, and then actually what you do, each build system defines its own attributes. So here you can define your easy configs that you want EasyBuild to build, options to pass to EasyBuild. Here I just did the same thing. You can have any options, or you can change the prefix, which by default is under the stage directory of the test, but you can place it somewhere globally, and then you get your software stack there. Then before running, you set the modules, and the build system, there is this utility property actually that will give you the actual module names that EasyBuild generated for you. And then you have your Sunday function, and it will run bzip2 minus help, and we just make sure that we get the right version. Similarly here with Spack, again, build system Spack, and you specify the spec. Behind the scenes, we use environments. So we create an environment and we do Spack add the specs, and we set the install tree to be into by default in the stage directory. Again, the whole thing to be standalone and without side effects. But again, you could set it differently to somewhere else. And imagine that you could store that in a variable. Here, define my Spack tree prefix, which you could set then from the command line. That's the nice thing, and how it connects with the previous. So moving forward, another feature that's pretty fresh is asynchronous execution of the build stage. So up to now, the build stage was executed serially. And that was a bottleneck, especially if you had many tests that you have to compile. So now we changed completely also the implementation of how we of the runtime. It's much simpler. Now you have basically two asynchronous phases. One is build phase, and the other is the run phase, where you have submitted your test. By default, since build by default happens locally, that is to where the frame runs, we limit that to 8 local build jobs. And even that can give you 30 to 40 higher throughput in a run that has many compilations. And that's a total that's the total gain in runtime. So which includes also the run phase later on and so on. So it's not just the build phase. And again, the other nice thing is that by setting build locally to false in your test or from the command line, you can instruct ReFrame to launch those jobs remotely on the target partition that you're building for. That's useful, very useful for when you don't have cross compilation, where you run the frame, but you want to submit your job. And then you get also the limits of that partition. And here actually is an experiment we run with all our production suite, which is about 700 plus test cases. And you can see, and we have actually 2 remote partitions with 100 jobs limit. And that's the limit we impose within the ReFrame. So we don't want to be more than, ReFrame will not allow to be more than 100 jobs either pending or running in that partition. And as you can see, we're constantly in that limit between also, and you can see from here, for example, you start with several jobs running and less submitted jobs for compilation, then all about 100 concurrent build jobs, then submitted. And yeah, here it must have been busy the system. So that's why you see this several things like stable. Probably we're waiting for an allocation. But it's a nice thing to show the how it progresses, the whole pipeline and the different internal stages. And yeah, so then is a new test naming scheme. Those that you have been using ReFrame, you remember those ugly names with parameters, that their values were kind of were encoded in the test name, which led to very big names. Now this is not anymore the case. Each test gets like a unique name, which is rather compact. And the way the test name is displayed is different. It's in a human readable form. And the other good thing is that the minus option matches also the human readable name, which is quite good. Now, to get the compact test names, you have to set that variable. By default is no, and the reason for that is for ensuring backward compatibility with dependencies, because dependencies, you're using the name, although I don't think that somebody has really constructed that name of a parameterized test to use it in a dependency chain, but nevertheless. So here shows like an example, and that also is a good introduction to my next slide about test libraries. So here is a test, Amber NVE check. It's a library test. And here we have a couple of parameters. And you see that this is like a parameter pack where it has the benchmark name, a value that's about the energy, and what is the expected threshold for matching it. And also it takes, if you can add in the parameter an optional argument that's called the FMT, which is a function that to format actually that thing, the parameter value. And in this case, we don't care about the energy and the energy threshold in the name of the test when we're displaying it. So we just return the benchmark name in order to format it. And then we have another variant here. And another thing here is our version of the Amber test CSS, which we add an additional dimension of parameterization where we want to test at different scales. And so eventually the test, as I'm showing here, is parameterized with 3 dimensions, and you get it. You get $sign parameter name equals the value and so on. So it's pretty nice and neat. Now, this brings me to the test libraries. I'll try to be quick. So I have hinted about it through that. So all these features actually make them make it. Let me just turn on the lights here because it's quite dark. So the auto detection feature, the composability is shown with parameters and variables, and the minus sets pave the path for this. So the idea is that the library test does not define anything that is site specific. It tries to see the test from a higher level point of view. How, for example, to run it, what parameters to add, perhaps different variants and so on. So it shouldn't define valid system, valid program environments, neither modules nor references and so on. You might define required variables if you want that somebody use it to specify something, and that could be important, but which you don't know how to set because you can't, that might be site specific. That's pretty valid for test libraries. I'm asking you to specify something, but you don't need to understand the whole test. That's the nice thing about it. And then you can set that from the command line. So we have like a work in progress experimental thing of library. It's in the repo under the HC test lib directory, and it's documented here, but the documentation, take it with a grain of salt, because it doesn't have it's a documentation from within the library tests themselves. So it's not on how to use it yet. So it's really work in progress. But here I'm showing an example where I'm getting the Amber NV check had before. And since it doesn't define valid systems, I define it for our GPU partition as find that one of my environments. And I'm defining here Amber, because in our case, the module to load is Amber. So load that, set the num task that's a required variable from the test. And then since there's, again, no filtering at the library level, I do the filtering here. So I'm selecting the variants of the test that use CUDA, because I don't want to run the other on the GPU partition. And then voila, I'm running it. Now, as soon as I've done that, I could get and run write my own site-specific test with all this information in, so that instead of typing all these things, I could just do reframe -n CSCS Amber check, as I've shown before. As I said, there's still work in progress. So we still need to figure out best practices in writing such library tests. I mean, as you write them, you understand, okay, how should I run? What's the best way to write this or the other thing? We would probably need generalizations for programming environments, or like attach properties to programming environments. Currently, although how you load the programming environment in ReFrame is part of the configuration, which is good. You can attach properties to that, but so far this is not standardized. And somehow, and the filtering doesn't happen on the properties. So it happens on the name of the programming environment. So you would have to encode those properties in the name if you wanted to filter and on the different properties. So that's something that we have been thinking of it, and it needs a bit of improvement. And then along the same direction that has come from various fruitful discussions within the community, you probably don't, I mean, instead of specifying valid system and valid prog environments, which can be very restrictive, you could make that like feature checks, either at the system level or at the programming environment level. So as future outlook, we definitely want to continue the work on libraries, and especially the test generalization. I think we have covered quite some distance since last year, because I really remember this being like a problem we have been discussing internally how to tackle it. And even coming up to conclusions that, okay, I mean, you can't have like generic tests. Yes, you can have generic tests, but you can write them in a way, in such an extensible way and layered way that you could possibly achieve the best of both worlds. Both having like generic tests, but also the site-specific tweaking of it without having to carry the load along with you. So I think libraries, I think, are something that's quite important. Another thing is that to support different test run scenarios, generally, I mean, in ReFrame, we have focused a lot in how you write tests and that composability, which I find quite powerful, but there are some test run scenarios that are quite useful when you actually use it to debug things or to do acceptance testing. So for example, although we have this flexible nodes allocation where we kind of submit, we automatically detect the free nodes of the system or all the nodes in a reservation, and we submit a job with n nodes. we don't have the use case, we don't have the support for generating multiple single node jobs to go on each of the nodes, which is very useful debugging tool and methodology. And similarly, stress testing the system, for example, where you would, for example, need a set of tests. You select the test based on what you need to stress, and have ReFrame run them for a certain amount of time repeatedly. This is not the case. I mean, you can kind of simulate it, but not. Yeah, it's not as if it were designed for it. Another thing is, as we move towards containerization and container times, there were also some interesting talks in this meeting. Currently, ReFrame can run containerized tests, but I think that part is not yet ideally designed, because actually you tie into your test. You say in your test which is the container runtime you're going to use, and you add there the commands, which practically it's not ideal, because ideally you would want the same test you run on a software stack that has Element, for example, and another software stack that has another module system, or in a system that just happens to have it in the path. You would, the same way you would take the same test and run it within a container without having the test to do anything else. So that's something we're gonna focus on. And then there is a branch, what we call for the text in the main repo, where we working towards 4.0. Practically, it's not something to be scared about, because eventually what is planned for 4.0 for the moment is basically all these deprecations that they accumulate. They have been accumulated last year, particularly. Eventually will be dropped, those deprecated features, and that would probably make 4.0. But we don't have yet a clear and definite timeline for that. So yeah, that concludes my talk. Again, thank you. And yeah, here is the information, documentation, GitHub, Slack community, Twitter, and that's it. Thanks for inviting us and hosting us, Kenneth.
Thank you for that talk. We'll have one quick question. I'm just looking at a nice. Going to ask Maxime to ask one of his questions. You can pick one, and then what we'll do after that is we'll create a breakout room so anybody who wants to ask some more questions, we'll move you into that while we prepare for the next talk.
So yeah, the first question I had earlier in your talk, you talked about automatic detection of processor topology. Can you go in a bit of details about how you do that? NUMA, CTL, proc CPU info, or things like that, and how it might interfere with C groups in a Slurm environment? Like, do you capture what's available to the job, or what's physically available in the node?
I think we capture what is physically available. I need to check that, because I think we check from sys devices, etc. I don't know if that is masked with C groups. I haven't tried that, but that's a good point, because eventually we tried different approaches with, like, we want like HW log, we tried, for example, and going towards this direction, but we ended up that it was changing and it wasn't consistent in the output practically. So we said we were gonna write our own detection on the same logic, which is what we did. But I need to check the code, but I think we're going on to the various files, such as like sys devices and down there. I don't know if this is masked by C groups. If it is, then yeah, we are aware.
Yeah, well,
if not, then
the files will probably tell you that you have 40 CPUs available, but the C groups will only let you run on 10.
Yeah.
So then you will
but
start
that's
more
an
threads
interesting.
than.
Okay. Yeah. Yeah, I'll take a note of that.
Okay, thank you. As I said, we'll create a breakout room, and if people have some more questions for Vasilios, we'll move you into that.
Okay, perfect.
So that we can set up the next talk, which will be Robert in about 5 minutes.
Okay, let me